We are going to practice electronic configurations, the abbreviated form, the complete electronic configuration, and those using the noble gas core, or and the orbital diagrams as well. And we are going to use not the memorized Aufbau process, but we obtain the electronic orbitals from the periodic table, right? So, meaning that depending on the atomic number, let's say 50, we will start from the beginning, right? And so remembering this is the S block, this is the first quantum level, second, third, fourth, fifth, sixth, seventh, and so on. And then just following it, right? So this would be, you fill the 1s first, then you're done, then you fill the 2s, this is the 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, etc., etc., etc. So for hydrogen, all it is, it's 1s, 1 electron, or the orbital diagram, which has just one hook representing 1 electron. Just write 1s under it. For helium, we have atomic number 2, so it's still 1s, which can hold 2, or 1s bar, hook up, hook down, indicating each electron has to have a different spin. Not using the noble gas core here because helium is the first noble gas. Lithium has atomic number 3, so it is 1s2, 2s1. Or now we can use helium, which is just 1s2 and then 2s1. Or let's just say 2s orbital single electron in it, just showing the noble gas core. Alright. Or you can also have the 1s included, hook up, hook down. Carbon has atomic number 4, so it's 1s2, 2s2. Carbon has atomic number 6. Okay, so you should get the periodic table out and follow what I'm doing. Locate carbon, find its atomic number 6, also equal to the number of electrons. We need 6 electrons, so 1s2, 2s2. Next is the 2p, and there are 2 electrons in it. For the abbreviated, you do helium, and then pick up with 2s2, basically just rewriting what I have already, 2p2. And so the point of that is also that we are focusing on the electrons that are in the outer shell, which are the electrons that engage in bonding. Those are called valence electrons, right? Valence electrons. They are the ones, carbon has 4 valence electrons. Those are the 4 that can do chemistry. They can do sharing or leaving, or you can gain electrons too. Okay. Fluorine has atomic number 7, so we will do 1s2, 2s2, and then 2p5. Or helium, 2s2, 2p7. Fluorine has atomic number 9. I may have said that wrong. It has 7 valence electrons. So, Scheibenkleister. Alright, so that's obviously a 5. The p can only hold 6 anyway, right? Alright. Orbital diagram, we would have the 2s filled and the 2p with 1, 2, 3, 5. Spread them out. That's Hund's rule, spreading out the electrons. 1, 2, 3, then you pair them up. 4 and 5, 7 valence electrons. Neon is a noble gas, so it is going to be 1s, 2, 2s, 2, 2p6 full. This is neon. Orbital diagram looks just like that, except you're going to put an electron in here with 8, right? Okay. One more time, this comes directly from the periodic table. We are just following the atomic number from 1 to 2 to 3, and so on and so forth. Oh, that's bonus right there. Anyway, 2s, 2p, 3s, and then don't forget this is the 3 here, not the 4. It's the 4th period, so 4s, 3d. Okay, let's do a few more. Potassium is atomic number 19. So we will do the abbreviated one. The noble gas right in front of it, which has atomic number 18, is argon. So we can write argon, put it in brackets, and then it's in the 4th period, so it's going to be the 4. It's in the s block, so it's going to be the 4s. Okay? So 1 electron, 4s1. Potassium has 1 valence electron. You want to do the orbital diagram, write 4s, and calcium is 1 over 20, so it's still argon, and then 4s2. Iron is a transition metal. It's in the 3D. So we still have argon, 18, right? Go find iron. It has 26 valence electrons. And then after argon, we fill the 4s. It's full. Then you fill the 3d. And you count. There's 1, 2, 3, 4, 5, 6, right? We've got 20 and plus 6, so 3d6. If we do the orbital diagram, we have the 4s, and I'm just doing valence electrons, which is filled. Then the 3d, there are 5 there. 1, 2, 3, 4, 5. And we have 6 electrons. Spread them out. Hund's rule. 1, 2, 3, 4, 5. And then you pair them up. 6. So that brings up another point. We have also magnetism that we can determine here. We can paramagnetic means unpaired electrons, and diamagnetic means paired electrons. So something like iron is paramagnetic because it has 1, 2, 3, 4 unpaired electrons. So that simply means it is paramagnetic. If everything is paired up, like in calcium, where the 4s, everything below it here is paired up, and the 4s is paired up, so that would be diamagnetic. What about valence electrons? Okay, so I told you the outermost shell, right? So iron, in this case, we have s and d electrons that are valence electrons. So we actually have 8 valence electrons. 8 valence electrons. The s electrons can leave. In fact, if you remember, I said that those two switch in energy. When iron goes to iron plus, right? When iron rusts, for example, it goes to iron plus 2 or plus 3. It loses the s electrons first, and then the 3d electrons. Looking at zinc, and then chlorine, and then argon. Zinc happens to be the last element in the 3d. Okay, so it's in the 4th period, but it ends in the 3d. So we still have argon. All right, argon, and then 4s2, and then 3d10. It actually has a full d shell. This is referred to as the pseudo noble gas core. I have another slide with that. I'll bring it back up. Okay, so this also happens to be diamagnetic. Everything is filled up. Okay, so the 4s is filled up, and the 3d is filled up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This actually does not have 12 valence electrons. The 3d, since they are full, they no longer can be removed. This has very good stability. And so the only valence electrons we have are the 4s. So zinc will only lose the 2 electrons here. Zinc really doesn't act like a transition metal either, because of the fact that it has a full d shell that is not reactive. Whereas copper, which is just one before that, has 9 d electrons, and it can lose 1 or 2 of those d electrons. We'll go. It's one of the exceptions, so we'll talk about that in a second. Chlorine is atomic number 17, so we back up and go to neon here. and then after neon it is the 3s, and then 3p5. Argon, of course, is argon, so I'll write the whole thing out, right? So argon has atomic number 18, so it's 1s2, 2s2, 2p6, 3s2, 3p6. All right, it is what that is. Okay, and then right, pretty straightforward. Okay, so I mentioned the pseudo-noble gas core already. Zinc, cadmium, and mercury have a pseudo-noble gas core. It boils down to having a full D shell, which makes the valence electrons only those of the s electron, right? So, and here it shows it shows the 10 here for zinc. Here it switched, it put the 3D lower like it should for the ground state. So this is in the ground state. And these are full and stable, so the only thing that can happen is these 2 electrons can be removed for zinc to turn into zinc plus, which is what it does. Zinc will be in the 2 plus. I will have a 2 plus charge when it engages in ionic bonding. Ionic bonding is when electrons are transferred from the metal to the nonmetal. So if zinc reacts with chlorine, zinc is going to be plus 2 and chlorine is going to be minus 1. Couple of exceptions. Chromium and copper are exceptions. If you look at the transition metals, chromium and copper are in the same group. Okay, they're on top of each other, and what you would expect is if you just fill in the 4s2, you expect that to be 4s2 3d4, right? And so it would be argon. That's what you expect. And for copper, you expect something similar. And never mind, copper, it's chromium and molybdenum that are underneath, and chromium and molybdenum will have the same thing. And then copper, you would expect to be argon, 4s2, and then 3d8. Sorry, 9. Okay. What happens here, there are two different reasons why this happens. One of them is spreading out the electrons, right? See, these are so close in energy to begin with, the 4s and the 3d. And so by promoting an electron into the D shell, we have a half full D shell, and we're spreading out the electrons. We're really relieving this pairing energy here, and it works out in this case. And copper is even more convincing because here we are promoting an electron to the 3D, pretty much containing or obtaining a pseudo-noble gas core, and therefore leading to lower energy, which means higher stability. These are just some things that you might have to memorize, that copper does that, and it's an oddity, and so does chromium. And it explains that copper has the tendency to be either +1, but it can also be +2. And then if you go down to silver, which is right below copper, silver can only lose 1 electron, and it's not going to lose 2 electrons. It will not give up its pseudo-noble gas core. This is just summary of what we've done already. If you do the electronic configuration using the periodic table, which is what we've done, you need to know the blocks, and you need to understand that the periods relate to the quantum numbers, right? N equal 1 is the first period, and so weiter und so weiter. Okay. I think we've practiced enough. Maybe we can do cerium. Cerium is one of those lanthanides. It'll be kind of tricky, right? You find cerium, it's atomic number 58. And so the noble gas that's right in front of it is xenon, which has 54. So we're not too far away. So xenon. Then we go to cesium, which is in the S block. And so that's the 7s, 1, 2, 3, 4, 5, sorry, it's the 6s, have to count, 6s, 2, and then after that we fill the cerium down there. So we've got 2 more electrons, and we fill the 4f, if you remember, 2. So xenon has 54, and cerium has 58. And if you have a periodic table, if you Google that, you'll find that there are some exceptions here that you'll actually see. If you look at the periodic table, now wait a minute, there's lanthanum there, which is 57. So you might think that it's 6s, 6s2, and then 5d1, and then 4f1, which is also correct. Okay, so there are some exceptions, and you actually will see some discrepancies. But whichever way you do it, the important is that you have 54 electrons and that you follow Aufbau or the periodic table method. Again, I've mentioned Hund's rule before. It's the lowest energy arrangement of the electrons in a subshell is obtained by putting electrons into separate orbitals of the subshell within the same spin before pairing electrons. Okay. Right. So what you want to do is instead of putting 3 electrons, these 3 orbitals, the p orbitals have the same energy level. So instead of doing this, you spread them out as shown below. Spread out the electrons, and then when you have to, you pair them up. And I explained that earlier by saying, well, if we have a 3p, a px, a py, and a pz, the electrons take up a lot of space. They're going to just spread out. They don't want to get into each other's way unless you have to. So when you go from nitrogen to oxygen, which has just 1 more, then you have to pair one of them up. So then they need to share. Okay? And mentioned paramagnetism too. If you draw out the orbital diagram, and this only works when you draw the orbital diagram, you look for single electrons that are not paired up. If there are any electrons that are not paired up, most likely it's paramagnetic substance. If they're all paired up, like any of the noble gases, krypton or calcium also has both electrons in the valence shell paired up, then you have a diamagnetic substance. And I'm going to take a break, and when we come back, I'll finish the chapter by talking about periodic trends. Periodic trends, we already looked at density and radius, but we're going to look into it in more detail.